multiple sheets, you can pass them all around. Just put the date on top. All right, let's begin. It's 35. So, can everybody hear me? I mean, I'm wearing a mic, right? Yeah. So here's where we were at the end of last class. We saw that neural networks are really powerful models which have taken over AI, tasks that were previously impossible using conventional machine learning and AI techniques, or nearly impossible, like human level or superhuman level speech recognition, or machine translation, or playing intelligent games like Go. All of these became feasible once we began using neural networks. They can actually even do things that were previously thought to be entirely in the domain of human intelligence, like captioning pictures or mimicry. They can even do creative stuff. So these models are really powerful. But then what are these neural networks? From where we stand, neural networks are just these boxes that take some input and produce some output. They are functions. So what we are really interested in is what is in these boxes. What are these functions about? And to try to compose these functions, we started off with the basis of intelligence, the human brain. In the human brain, these functions are computed, in human beings, these functions are computed by the brain. And so neural networks in their basic form try to mimic the network structure in the brain. We saw all of this in the last class. And we also saw that the brain is a network of neurons, where the individual neurons have the structure on the left. Each neuron has incoming connections from many neurons. When the aggregate input exceeds some threshold, the neuron fires, roughly speaking. This is not exactly how a neuron works, but this is a reasonable approximation to it. And so that the neuron... No.
Did somebody get this red button over there? That side?
No, nobody's been that side.
Just so you know, if you hit this button, that notifies us as an emergency mode.
Thank you. We will watch out. Yes. Amazing. So we saw that neural networks in there, that the human brain is this giant network of neurons. And the neurons themselves are these little units we have to the left, which have lots of incoming connections. If the aggregate input exceeds some threshold, the neuron fires. That signal goes down this long arm called the axon out to the neurons. And so artificial neural networks try to mimic this structure. This is all from the last class. Artificial neural networks are networks of computational models of the neurons. And the computational model of the neuron is this perceptron to the left. My sword is missing. I could point. The neuron receives a number of inputs. Corresponding to each input is a weight. And if the weighted sum of all of the inputs exceeds some threshold, the neuron fires. Otherwise, it does not. So this mimics the operation, or the crude at some crude level, it mimics the operation of the of biological neurons. So from a mathematical perspective, we can express it like so. The neuron produces binary outputs. The output is either 1 or 0. And if the weighted sum of the inputs exceeds a threshold, the output is going to be 1. Otherwise, it's 0. So the neuron fires if the weighted sum of inputs exceeds a threshold. Otherwise, it does not. And electrical engineers amongst you will recognize this as a threshold gate. So we also saw that we can draw this slightly differently. Instead of trying to think of it as the weighted sum matching some threshold, we can think of it as the weighted sum plus a bias term. And we can think of it as a threshold activation operating on a weighted sum plus a bias term. So what did we call a weighted sum plus a bias? Anyone remember? It is an affine function. So the neuron can be thought of as a threshold activation that operates on an affine function of its inputs. And now, once we model it like so, then we can sort of deviate away a little bit from these threshold activations and have other kinds of activations like the sigmoid, which is a soft version of the threshold. And you can now say that the neuron really consists of some kind of an activation function, some nonlinear activation function. It could be linear. We'll see why, what the difference is later in the course. You can think of it as some activation function that is operating on an affine function of the inputs. So, like the sigmoid, you can have all of these other activations. You can have the tan H, which is just the sigmoid, which is scaled and shifted. The rectified linear unit, which replicates the input if the input is positive, but outputs are 0 otherwise. Or the soft version of it, which is a smooth curve, which is called the soft plus. All of these activations are also possible. Now, this is where we sort of left off in the last class. We saw a lot more. We'll revisit some of it. But for the purpose of this lecture, I'm going to continue to assume that the activation function is a threshold activation because it makes some explanations simpler. We will come back to non-threshold activations towards the end of the lecture. So first, as always, you have these, here's the poles. Pole number 93. Time into 60 seconds, right? Seconds, folks. Close it. Quick. I think we are done. All right. So I hope all of you managed to get it in. Of course. The poll was about making the distinction between linear and affine combinations. So 3x plus 7y, that's a linear combination of x and y. Everyone agree? Right? 3x plus 7y plus 4, is that linear? No. And so what was the characteristic of a linear combination versus an affine? You don't have the bias. If you equate it to 0, what's the difference between the two? Alex? What was the difference between the locus of between the plots you'd get if you equated a linear combination to 0 versus an affine? The plot, if you plotted it.
If I equate a linear combination with an affine, I get like a straight line.
What was the difference between the linear and the affine? Yes? It goes through the origin, right? The linear combination goes through the origin. The affine combination does not, is not required to. So 3x plus 7y is also an affine combination because an affine combination, a linear combination, is a special case of an affine, and 3x plus 7y plus 4 is affine, right? Anyway, continuing on. So a multi-layer perceptron is a network of perceptrons where perceptrons obtain inputs from other perceptrons, and their outputs go to other perceptrons. So this entire network is a computational unit which takes some input and computes an output. It could compute a single output, like in the figure to the left, or it can compute a bank of outputs, like in the figure to the right. So now we are here in a deep learning course. So we're speaking of depth. What do we mean by depth. When we are speaking of a deep model, we are speaking of a deep network. And what is a deep network? Is there an official definition for a deep network? There is. So deep structures in general are well defined. If you think of any directed graph, a directed graph is a graph where all the edges have a direction. Information goes from one end to the other and not the other way around. So in any directed graph is going to have source nodes and sink nodes. It could be loopy, but in any directed graph with source nodes and sink nodes, a source node is a node where all the edges are going outwards. A sink node is one where all the edges are coming inwards. So in any such directed graph, the depth of the graph is the length of the longest path from a source to a sink. So here, for example, this graph has one source and a sink. There are two different paths from the source to the sink. One is 1 hop long, the other is 2 hops long. This graph, what is the depth of this graph? 2. What about the one to the right? 3, right? Because although you have this path of length 1, the path of length 2, and the path of length 3, the only one that counts is the longest path. So this is a depth 3 graph. Now, we will say any graph that has a depth greater than 2 is deep. That's the technical definition. Any graph that has a depth greater than 2 is deep, and a neural network is just a graph. You have all of these units. They're getting inputs from other units. They're sending their outputs to other units, right? So it's a graph, and it's a directed graph. Information is flowing from the input to the output. And so if you look at this figure to the right, that's a neural network. This is the input, so there are really no units over here. But you can think of it as units. So nodes. What is the depth of the neural network to the left? Chen? Is it 4? Maxwell, what's the depth of the figure to the left? 3, right? Why?
So it's at the bottom layer, at the gray ones, go 1, 2, 3 up, and you have the orange one, which will only down.
So the length of the longest path from the bottom to the top is 3. So this is a depth 3 network. Now what about the one to the right? Each box is a layer. So the top right, what is the depth of that one? Saida? Is that 3? It's 2, right? What about the one in the middle with the cat? You there? I don't see a name. You should keep it in front of you, Mia. So what is the depth of that one? Is it 3? 4, okay. So you get an idea. But then we also speak of layers. Can anybody tell me how one defines a layer? Anybody can anyone take a guess as yes, Minwei?
All the nodes are at the same depth.
With respect to? From the source, right? So she's right. All neurons that are at the same depth with respect to the input are considered one layer. So you can see that in the figure to the bottom right, all the red neurons, what is their depth? Which layer is that? First layer. What about the green ones? Second. The yellows? Third. But then Y is, now the yellows are a depth of 3. The blues also have a length 3 path from the input to the output. Why are they not part of the third layer? It's not the longest path. The longest path is depth layer. It is 4 steps long, right? So you get an idea of what depth really means. So now we've defined our definitions. Now we also saw that in a multi-layer perceptrons, these things actually compute functions. They can produce a single output or many outputs. The inputs can be real or Boolean. The outputs can be real or Boolean. And we saw that they can compute all kinds of functions. But we sort of hand-waved a bit. Are there any restrictions, and how do these restrictions actually relate to the structure of the network? What kind of input-output relations can this network actually model? And so,
Professor,
yeah,
I have a question about the previous slide.
which one?
Is there any reason why, like, there are multiple sources? Or is this just like a partial graph in like most cases?
There are multiple sources over here.
Okay.
I mean, in a neural network, every component can be thought of as a source, right?
But like, what are those multiple sources?
So if I were to give you an image, every pixel is going to go into one unit, right? One input.
Oh, I see.
Those are all the sources in the graph.
Okay, so it's just like one source per input.
One source per component, input component. Okay?
I have a question for previous slide also.
Yeah.
So you said the depth for the left one is 3.
Yeah.
So we don't count the input.
It's the path. The input is the source. The output is the sink. The length of the path, right? Okay. So we saw that MLPs can compose all kinds of functions. They are universal Boolean functions. They're universal. They can compose any real valued functions. But what are the limitations? That's what the topic for today is going to be all about. And now we're going to look at multi-layer perceptrons as universal Boolean functions and why depth is necessary. We're going to look at them as universal classifiers and why depth is necessary. And we're going to look at them as universal approximators. And again, why depth is necessary. And then we're going to have a brief discussion of optimal depth versus width. I will not be talking about RBF networks, but please look them up because they're an interesting topic. So let's start with Boolean functions. We know that MLPs can model Boolean functions, but how well can they do it? Let's start with a simple perceptron, which is the smallest network. It's just one node. We know that a single perceptron can compute ANDs. That's the one to the left, top left. They can compute an OR, like the one in the bottom. They can also negate the input, like the one to the top right. So with this we saw in the last class. But we saw, but this is not all that a perceptron can do. A perceptron is a ridiculously powerful little unit. So for example, over here is a perceptron that will fire only if the first L inputs are all 1 and the last L inputs are all 0. Otherwise, it will not fire. To see why this is the case, let's just actually set the inputs to the right value. So this is 1, 1, 1. There are L of these, 0, 0, 0. The remaining are zeros. If the weights are for all of these are +1 and the weights of these are -1, right? What is the total input that comes in? N? No. So the first L are 1, the rest are 0. L. Can I hear this out aloud? Everybody sleeping? In chorus, 1, 2, 3, go. Thank you. Right? I don't want you to sleep. Now what happens if I flip one of these guys?
Less than L.
That's less than L. What happens if I flip one of the higher guys? Again, less than L. This only fires under the very specific condition that the first L are 1 and the second L are 0, right? Now, so this is a universal AND gate. You can have some fairly complex functions. Here's a different one. This fires if any of the first L are 1 and any of the remaining, or if any of the remaining are 0. Why is that the case? First, let's reverse the logic. Let's set it in the one condition where it will not fire. When will it not fire? Can you tell me? Yeah.
It's a 0, then all else are 1.
Yeah, the first L are all zeros, and the remaining are 1, right? To N. In this case, considering that these weights are -1 and these weights are 1, what is the total input that comes in here? N, L minus N, right? Because you have N minus L of these guys, and each of them has a weight -1. So you have L minus N. I do not want it to fire over here. So what do? I add 1 to the threshold, right? +1. And now, if any bit flips, it's going to match the threshold, and it's going to fire, right? So you can see how powerful this little unit is. Or you can do something called the majority gate. This one will fire. It's very obvious to see why if at least k of the inputs are 1, right? So you can actually use a single perceptron to determine if the majority of inputs are 1. That's why it's called a generalized majority gate. Now, if you want to do this with a Boolean circuit, the Boolean circuit becomes exponentially large. If you're only using standard Boolean gates, you can do this with one perceptron, which is why Frank Rosenblatt got confused. He thought this could do everything, and you got those crazy headlines that we saw in the last class. But the reality is, one perceptron is not enough. You can't even do something as simple as an XOR. To do an XOR, we need a multi-layer perceptron, networks of perceptrons. So a multi-layer perceptron, we saw, can compute the XOR. The multi-layer perceptron requires 3 neurons, 2 in the first layer, compute, XOR Y, not XOR, not Y, then you add the 2. But in fact, it turns out you can do it with only 2 neurons. I got this circuit from Gerald Friedland in Berkeley. I'll leave it to you guys to figure out why this computes an XOR. But now the weights are no longer 1 and minus 1, right? So you can do this with 2 neurons and 5 edges. Now, anyway, given that a perceptron can compute any Boolean gate and more, we can begin computing some fairly complex Boolean functions with multi-layer perceptrons, like these guys, right? This ugly, hideous function. In fact, the fact is you give me a Boolean function, and I can construct a multi-layer perceptron which computes it. That's why MLPs are universal Boolean functions. But then, in this example, for this hideous Boolean function, how many layers does that network have? You there. How many layers does the network have? The very corner, yes. 3. May I see your name?
My name is Laura.
So, and him, what about? Pardon me? Connor. Okay. Thanks, guys. So, if you're in the corner, you're more likely to be invoked simply because you're in the corner. Anyway, so given any odd Boolean function, how many layers do you think the network will require? How does the complexity of the function relate to the number of layers that are necessary to compute it? Ameya, can you take a guess? So here is my claim, and I will show that it does not matter what the complexity of the function is. I can compose it with a multi-layer perceptron that has only one hidden layer. Why is that? Any Boolean function can be written as a truth table. How many of you don't know what a truth table is? Raise your hands. Thankfully, nobody has. Okay. So a truth table is simply a listing of all possible input patterns with its output. And you don't even need to show all combinations. You only need to show the specific combinations for which the output is 1, because for the rest, the output is implicitly 0. Now, once you write a truth table like this, then look at the first row. The first row says the output is 1 when x1 is 1, x2 is 1, x3 and x4, x1 is 0, x2 is 0, x3 and x4 are 1, and x5 is 0. If I were to write a Boolean clause for this, this is not x1, not x2, x3, x4, and not x5. So there are, in this case, 1, 2, 3, 4, 5, 6 clauses. And so this entire truth table can be written as a DNF formula with 6 clauses. The pluses represent ORs, and one of the clauses each clause represents one of the input combinations for which the output is 1. But then now when I write it like this, here's how I can actually compose my MLP. I have one perceptron for the first clause, one for the second, one for the third, one for the fourth, one for the fifth, one for the sixth, and a final one to add them all. It doesn't matter how complicated the function is. When I express it as a truth table, I can write a DNF formula of this kind, and I can compose a multi-layer perceptron which has only one hidden layer, basically only 2 layers. So a one hidden layer multi-layer perceptron is a universal Boolean function. But then, if I want to do it this way, What is the largest number of perceptrons that I will require in that one hidden layer? What is the worst case if I want to do it with just one layer? Shreya, can you guess? What is n? Yeah, you were saying? And what is the number of ones? I'm speaking of the worst case.
N squared.
N squared. Okay, let's take a look, right?
2 power n, sir.
2 power n. There you go. It's going to be exponential. Why? So how many of you are familiar with Carnot maps? Raise your hands. How many of you have never heard of a Carnot map? All right. So a Carnot map is a topological representation. Maxwell, I thought you would know. Okay.
Can we do like even at -1 and then do that one where you
Thank you. Yes, we will get there. Right? Maybe you should be here. All right. So, all right. So here it is. The Carnot map is a topological representation of the input space. Now, in this case, I have a Carnot map of 4 inputs. The rows represent every combination of 2 variables, w and x. The columns represent every combination of y and z. And you'll observe that that any 2 adjacent columns differ in only 1 bit. Now, the leftmost column and the rightmost column actually meet, although I've unrolled them. The topmost row and the bottommost row also meet because they only differ in 1 bit. So the sheet actually represents a donut. It's a torus. And it's a topologically accurate representation of the relationships between the bit strings, the bit patterns. Vila? Aha. I need this so I can point. Okay. So this is a topologically accurate representation of the bit strings. And every cell over here represents one combination of bits. So this one, for example, is wx is 1, 0, yz is 0, 1. So this is 1, 0, 0, 1. And each highlighted cell represents one bit pattern where the output is 1. So here there are 7 combinations of the inputs where the output is 1. And so a basic DNF formula would require 7 neurons in the hidden layer. But then I can do something smarter. I can begin grouping things up. Why so? If you look at these if you find any boxes that are adjacent, they can be grouped up. So these 4 over here, these 4 can be grouped because what this means is that regardless of the value of w and x, so long as x and y, y and z are 0, 0, the output is 1, right? So I can just write one clause, not y, not z, and that combines all 4 boxes. Similarly, these 2 guys, they can be grouped because it says that so long as w and x are 0, 1, and so long as y is 0, the value of z doesn't matter, right? And so that becomes one clause, not y, not w, x, not y. And similarly, these guys at the bottom to the extreme right, they can in fact be combined with the other 2 corners, and you're going to get one clause. So when you can begin grouping things in this manner, then even if the truth table is large, you can sort of begin zapping your formula down and make it very small, and your network is going to be very small. So in this case, the MLP that is needed for this formula has just got 3 neurons in the hidden layer. What arrangements of 1s and 0s simply cannot be grouped together? You? What's your name? Yeah, sure, okay. So what arrangement of 1s and 0s cannot be grouped together? Pardon me? Diagonal, you, the lady there. Yes, what's your name?
Is it a diagonal?
Is it just diagonal? Anybody else want to take a guess? Yes.
Like you have all the ones spread out like checkerboard.
Singular elements.
Pardon me?
Singular elements. Just alone.
Anyone else?
Checkerboard.
Checkerboard, right? This simply cannot be grouped together. No 2 elements, no two adjacent elements have the same value. How many neurons will I require in my first hidden layer for the MLP over here? 8, because there are 8 boxes, right? So the DNF formula is going to require 8 clauses, and I will need 8 neurons in my one hidden layer. So here is a 3-dimensional version of a Carnot map. It has how many neurons will I require in my hidden layer? Yijing. How many? Pardon me? 24? How did you get 24 from this? Yes, Owen.
You have 2 to the 4 half.
So this is a 64 cubes. This has 64 cubes. Every alternate cube is a 1. So how many will I need? 32, right? Everybody say it aloud. So everybody registers to everyone. Come on, 1, 2, 3. Thank you. I've got to wake you guys up. We'll do this all class long. Now, can I generalize it? Someone mentioned this. In general, if I have n inputs, in the worst case, I'm going to require 2 raised to n minus 1 perceptrons in the hidden layer. This is exponential in n, right? Does anybody recognize this function? Okay, I'll tell you the answer. Wait, there's actually a code. Manish, time it, huh? Time कर रहे हो ना? By the way, don't forget to sign up on the sheets and turn them over, right? 10 seconds to go. Right, close it. Right, close it, Manish. Yeah. So if I have 10 inputs, 2 raised to 10 is 1024. Half of that is 512. So I'm going to need 512 neurons in my hidden layer, right? If I want to do this with more than one hidden layer, how many neurons will I need? So to give you the answer, I'm not going to hold you in suspense. This function to the left is just an XOR. It's W XOR X XOR Y XOR Z. The function to the right is also an XOR. It's an XOR of all 6 variables. Anytime you have an XOR, it means the 2 variables must always take opposite values, right? And so this means, remember, this is how we could compose an XOR with 3 neurons or even only 2, right? Here's how I could compose the network for this guy. I have an XOR with 3 neurons for the first pair of for the first pair of variables. Then I can XOR that with the next variable, and I can XOR that with the next variable, and so on. So if I have n variables, I need n minus 1 XORs. Each XOR needs 3 neurons. Actually, it only needs 2, as we saw. So 2 times n minus 1 neurons will do the job. Or in this case, this is an XOR of 6 variables. And so I can just arrange them like so. And I can do this with only 15 neurons, as opposed to 33. So in general, an XOR of n variables is only going to require 3 times n minus 1 neurons, or even less, 2 times n minus 1 neurons. That is linear in the number of inputs, provided the network is allowed to be deep, right? What are the restrictions over here? So here's the general statement. If I allow only one hidden layer, I'm going to need the size of the network is exponential in the inputs. If I allow arbitrary depth, the size of the depth net is linear in the inputs, right? And in fact, these linear in the inputs layers, neurons can be arranged in only 2 log n layers. Why is that? Why is it that I can arrange it in 2 log n layers? The XOR is associative. What do I mean by associative? I can group the variables anyhow when I perform the operation, right? Everybody, does anyone not remember the meaning of associative operations? Anyone who doesn't know what associative means? I hope not to encounter one in class. Okay, so what this means is that I can group the variables pairwise, and I can compute an XOR of each pair of variables. So if I have n variables, I'm now going to end up with n minus n over 2 outputs. Now I can XOR those outputs pairwise, and they're going to give me n over 4 outputs, and then I can XOR those out pairwise all the way until I have only one output. Now at each stage over here, the number of variables is reduced in half. So this means, if I have some k variables, and if I have the stage-wise grouping where at each stage the number of variables reduces by half, how many stages can I have? What's your name?
Jesse.
Jesse. Yeah. So if I have k variables which are grouped pairwise, how many stages can I have?
Then it'll be log of k.
Log of k, right? And since each XOR needs 2 layers, I'm going to need 2 times log base 2 of n layers, right? Now what happens if we was comparing one hidden layer versus arbitrary depth. What happens if I say, I'm not saying one hidden layer, is there some intermediate compromise solution? I'm going to have 3 hidden layers. How does that help? Okay? And here's what happens. If you look at this problem, if you see that if I decide to terminate this network with only k layers, where k is any number, it doesn't have to be 1, then when I begin going up, from the kth layer on, I still have a bunch of variables that must be XORed. And when I have a bunch of variables that must be XORed and I'm only allowing one more layer, how many neurons will I need in that layer? Sichi? Anyone want to guess? Raise your hands if you have the answer.
Is it 2 power m minus 1?
Whatever, 2 power n minus k.
M minus the number of XR
You guys have to look at the slides. I mean, this is horrible. You're neither listening to me nor watching the slides as far as I can make out. The answer is right here, right? The output, if I terminate it after only k layers, each layer, each pair of layers is going to reduce the number of variables by half. So after k layers, I have 2 raised to n minus k over 2 variables, which must be XORed. And the number of neurons in the next layer is going to be exponential in that number. And so you're still going to require order 2 raised to some c times n neurons in the network. So what this means is that any time you have a fixed depth network, regardless of the size of the input, that network will have to be exponentially sized if you want to capture the worst case functions. Any questions? You guys in the corner there? So now, when we speak of the number of parameters in a network, it's not the number of neurons, it's the number of weights. But the number of weights is quadratically related to the number of neurons. So anytime you have a fixed size network, then the number of parameters required to represent an arbitrary function is still going to increase exponentially with the number of inputs, right? And so deep Boolean MLPs that scale linearly in size with the number of neurons can become exponentially large if recast using only one or even a fixed number of hidden layers. That's why we need depth. And so here's a summary. An MLP is a universal Boolean function. It can represent any given Boolean function, but only if it is sufficiently wide and it is sufficiently deep. You can trade off depth for exponential growth of the width. But if you restrict both width and depth, you may not be able to model your function at all. Does that make sense to everybody? Questions? Anything on Piazza? Okay. So here's the story so far. Multi-layer perceptrons are universal Boolean machines. Even a network with a single hidden layer is a universal Boolean machine. But a single layer network may require an exponentially large number of perceptrons. So deeper networks may require far fewer neurons than shallower networks to express the same function. They could be exponentially smaller, right? So now let's go on to the next topic, which is MLPs as classifiers. We saw that an MLP is can be a Boolean function over the space of reals. What this does is that it can output a 1 for some regions of the input space and a 0 for other regions of the input space. So if you combine this, you can think of this as a classifier which produces 1 for some inputs and 0 for the others. And the boundary between the two is the classification boundary. We saw an MLP can model any arbitrary classification boundary at all. It can find, regardless of the complexity, given it can, but then what are the restrictions? So to understand these again, let's go back to the simplest MLP that we can think of, which is the simple perceptron. And again, we saw that the perceptron is simply a linear classifier. It models a Heaviside function. There is some hyperplane, and any input to one side of the hyperplane is going to produce a 0. Anything on the other side is going to produce a 1. If the input is two-dimensional, then the plot for the output of the perceptron is going to look like the one to the bottom right. It's a step function. And now that we have a perceptron which can model this, we saw why we can model Boolean functions. Any Boolean function. Boolean functions, if you have a Boolean function of 2 variables, the possible input combinations are shown by the 4 circles. If I constructed a perceptron which output a 1 for the 3 in the upper corner, then that's an OR. If I constructed something where which output a 1 only for the lower half of the page, it was negating one of the variables. And you can see why you cannot do an XOR. An XOR has to produce a 1 for the upper diagonal, but zeros on both sides. This means you want the function to go up and then come down. And clearly, a simple linear classifier is not going to do this, right? And so there's a poll. Five seconds? 10 seconds? Okay. All right, 10 seconds, guys. This is an easy one. Stop it, okay? So we said an XOR network needs 2 hidden neurons and 1 output neuron because we need 1 hidden neuron for each of the 2 boundaries and to OR it. That's why we needed the specific structure that we have, right?
I have a question. Isn't you just show us there's a 2 neuron structure?
Tell me, can you guess how that happened?
He must modify the average.
No, here's what happens. If I have something like this is an XOR, but if you're only looking at Boolean outputs, this is an XOR as well. Right? You can have the 2 boundaries intersect in some useless region of the space because the input is Boolean. And so you can get it with 2 neurons. Once you begin looking at it in this way, in these terms, it becomes very interesting, the kinds of things, how you can model different things, right? So I was expecting someone to ask me that question. And now we saw how we can model more complex decision boundaries, like this pentagon. We saw that we can do this by having 1 neuron for the bottom, 1 for the left, 1 for the top right, 1 for the top left, 1 for the right. Okay, I think right? And then you can OR the lot, right? Now here's what, I want you to observe this carefully. What happens when the input is inside the pentagon? What are the values of all 5 of these variables? Ryan? So what would the sum be? So if I use a threshold of 5, what will the decision boundary be? It's just going to be the pentagon, right? That's the only region where all of them are 1 and the sum is 5. So now, what about you? You boys there, I don't see your names. So that, Shiva. If I use a decision boundary or a threshold of 4 in my final output neuron, what is the decision boundary going to look like? It's going to be a star because all the 4s are included as well, right? And so this matters, but we'll see how. Anyway, having seen this, we saw how we could model more complex decision boundaries. I can make a double pentagon by having one subnet for the first pentagon, another for the second, and then I can OR the lot. So an MLP is going to capture this. Or I can capture these absurd decision boundaries. And the way I would do it is, if I wanted a decision boundary like the one to the left, I can chop it up into little polytopes. I can have one subnet for each polytope, and then I can OR the lot, right? These are multiple layers. How many layers do I have over here? Shreya, how many layers do I have? Speak up. 3, okay. So guys, when I ask questions, somebody has to yell out, otherwise I'll pick one of you. And probably I'll end up calling the same person again and again because I memorize their names, because I can't see your names, okay? So here's my question. Can I do this with just one hidden layer instead of 2? Or let's take something simpler. Can I do this double pentagon with just one hidden layer? How many of you think it can be done? Raise your hands. All right. Okay, so Mrinmai, how would you do it, considering that you think it can be done?
Well, I just thought because MLPs are universal, I could model any.
That's actually pretty good logic, but how? Anybody else? So you there with the orange hair. The second, yes, I don't see your name. So just tell me your name. Justin, okay. How would I do this with just one hidden layer? Do you guys have a guess? Yeah. So it's not simple, and I'll tell you why. And that has to do with the fact that if you look at these sums are 5 inside the pentagon, but 4 just outside, right? So if I try to compose 2 pentagons directly, each of them has these 4 regions, which are not required, but they sum up to 8. I'm going to get a lot of spurious regions. It's not trivial to do this. So how would I actually do this? To see how I would do this, I'm going to go down to start off with a simple figure, a diamond. Now, a diamond can be done with 4 hidden neurons. And if you look at the sum, the figure to the right plots the sum. And you can see how different thresholds will give you different decision boundaries, right? The sum is 4 inside the diamond. But the region, the area where the sum is just below 4, where it's 3, is, what is that area? What's it, Zevin, is it? Yeah. So what is that area of the 3 over here? The yellow region. What is, if you had to put a number to it? Yuan. The area is infinite, is it not? It's going all the way to the end. So the area where, when I am forming a diamond, the area where the sum is just below the threshold is actually infinite. When I compose a pentagon, what happened to the area where the sum was just below 5? These became triangles, these are finite, right? Then when I compose a hexagon, they became smaller still. Keep looking to the figure to the right where I'm plotting the sums. So what do you think will happen in the limit? Maxwell, this is for you, as I keep increasing the number of sides. It's going to go to 0, right? Thank you. So here's what will happen. This is what happens with 7, a heptagon. And you can see that the region where the sum is 6 has become smaller. The region where the sum is 5 is now a 7-pointed triangle. And the bottom, it's either 3 or 4. This is with 16 sides. This is with 64 sides. This is with 1,000 sides, right? And as I keep increasing the number of sides, the area within the central region is going to have a sum of n. And the area where the sum is less than n and not equal to n over 2 is going to keep shrinking. And you'll eventually end up with only two regions where the area is either n, the sum is either n, or n over 2, and a very steep fall off between the two. You can actually work out the math and you get this cute little equation. But then a simple way to think about it is you can approximate it as like so. That when you have a very, very large number of sides, then the sum of their outputs is going to be n within the central region and n over 2 outside. So I can just add a bias term which subtracts n over 2. And now the sum is going to be n over 2 inside, and what will it be outside? Kelsey, 0, right? Now, suppose I want a decision boundary that is two disconnected circles. How would I do it, Kelsey? Can anyone? Yes.
Just OR gate again.
OR gate of what?
So that's a MLP that computes whether a point is within a circle, and then so you can just have two of those, and then whether it's
and I want only one hidden layer, right? But you're pretty much on it. So here's what I can do. If I take two such subnets, each of one computing a cylinder, and then I sum their outputs, what is the output going to look like? You there? What's it going to look like?
I think might be n minus 2. It will be 0 just outside both of the circles.
Both of the cylinders. So I'm going to have the figure is going to be just two cylinders, disconnected cylinders, and 0 everywhere else. If I use a threshold of n over 2, what will I get? The decision boundary. So that's what the figure looks like, right? The top right. If I slice it at a height of n over 2, what's the decision boundary going to look like? Prithvi. Two disconnected circles, right? And so I've shown you how I can compute a decision boundary of two disconnected circles using just one hidden layer. And so now if I want to compute this polygon, multiple polytope, what I will do is fill it up with circles. I can make the circles arbitrarily small to make it arbitrarily precise. And is it ever going to exactly model the double polygon? No. But I can get it to the level of approximation that I'm comfortable with. Right? So the MLP is a universal classifier. It can capture any classification boundary. A one hidden layer MLP can model any classification boundary. So MLPs, even a one hidden layer MLP is a universal classifier. But then here is the problem. This double pentagon, if I allowed myself just 3 layers as opposed to 2, the number of neurons required was only 13. In fact, I can do it with fewer than 13. Whereas if I restricted myself to 2, how many did I need? Say it out aloud, everybody. How many do I need with just 2 layers? Infinite. Say it, everybody, aloud. Thank you, right? Otherwise, So, and so you can see how and in terms of accuracy, the infinite 2-layer network, is that 100% accurate? What about the 13 neuron 3-layer network? It's 100% precise, right? So you can see why depth matters yet again. And so, going back, how does depth relate to the complexity of the pattern of the classification boundary? Can anybody take a guess? Anyone? Saida, if I asked you to guess, what would you say? Can you speak up louder, please? What will require? When? So if my classification boundary is complex, the more complicated my classification boundary is, the fewer neurons I will require as I make the network deeper. If I restrict the depth, the size of the network required to model it accurately may just blow up. Right? So we've sort of, I'm going to also take a look at a different worst case decision boundaries for threshold activation networks. Now let's take a look at this decision boundary. I want an output of 1 in the yellow regions and a 0 outside. A naive one hidden layer network is going to require infinite neurons, right? If I do it with 2 layers, I can do it with 56 hidden neurons, 57 neurons in all. Why 57? Because this pattern is formed of 16 lines. So here are the 16 lines that form the pattern. So I will need 16 neurons in the first layer to capture these 16 lines. Now there are 40 yellow regions in the figure. So I can compose those 40 regions using 40 neurons, which build off the outputs of the 16 neurons in the first layer. And then I can OR the lot. So the total number of neurons required if I have 2 hidden layers is 57. But then here's something. This is just an XOR pattern. We're familiar with this, right? This is an XOR of all 16 outputs. And so because this is an XOR of all 16 outputs, I can actually compose it with an XOR network. And an XOR over 16 outputs is going to require 15 times 2. It's done. I mean, I don't even need 3 neurons per XOR. So it's going to require 30 plus 16, 46 neurons will do it. Whereas otherwise I needed 57 neurons, right? But then, the difference doesn't seem very dramatic. Let me show you something a little more complex in just 2 dimensions. This is a grid formed of 64 lines. The network must output a 1 for all the yellow regions. There are 64 basic line detectors, and there are 544 yellow regions. So the total number of neurons is going to be 544 plus 64 plus 1. If I do it with naively with just 2 hidden layers, and so it will require 609 neurons. But then again, this is really just an XOR, and if I do this as an XOR over 64 variables, then I can do this with just 190 neurons. So now the difference going up from the first example to the second suddenly became much larger. And in general, as you increase the dimensionality of the input, now these are simple 2-dimensional toy problems. Your real-world problems are going to be thousands of dimensions. You can imagine what happens and how depth really matters, right? So you're never going to work with 2-dimensional problems, but 2-dimensional problems are great for illustration. So the number of neurons required in a shallow network is potentially exponential in the dimensionality of the input. This is the worst case. Or alternately, exponential in the number of statistically independent features in the input. So here's the story so far. Multi-layer perceptrons are universal Boolean machines. Even a network with a single hidden layer is a universal Boolean machine. MLPs are universal classification functions. A network with a single hidden layer is a universal classifier. But a single hidden layer, that should be a single hidden layer network, may require an exponentially large number of neurons. Deeper networks may require far fewer neurons than shallower networks to express the same function. They could actually be exponentially smaller. So what this means is that deeper networks are more expressive. They can compose more complicated functions for the same number of neurons or the same number of parameters. Right? Questions, anybody? Yeah.
What's the difference between universal classifier and universal Boolean function?
So a universal Boolean function is going to be able to compute any Boolean function over Boolean variables. A classifier is essentially a categorical or a Boolean function over reals.
Say that again?
A classifier, the way we're describing it, we're trying to assign classes.
Yeah.
So the output is categorical, 0, 1, 2, 3, and it typically operates on reals.
Oh.
Right? Yes. You raise Abhi.
Can you explain the XORs, that diagonal XOR map thingo again in a little bit more detail? I don't think I caught
This
it.
one?
Yeah. Why does it require 253 neurons exactly?
So This one, there are 64 variables. So it requires 3 times n minus 1, 3 times 63.
Oh.
Right? I think that's 253, right? Or maybe I'm wrong.
Oh.
Right?
It's just 3 times 63 minus 1.
3 times 63 plus the original 64.
Oh.
Right? So that gives, yes.
So since the deeper network is less neurons, then can we just make the network deeper and true?
Okay, thank you. You're leading to the next stage of the lecture. So before that, let's look at neural networks as universal approximators for real functions. We'll get to your question very quickly. We saw how we can model a little step function on a scalar variable using 2 neurons, one with different thresholds. And we also saw how we can use this to model any arbitrary scalar function of a scalar variable by slicing up the range and having one subnet producing a step in each portion of the range, right? And then scaling the outputs and summing them up. So one hidden layer MLP can model an arbitrary function of a scalar input. But suppose I went up to multivariate inputs, multiple dimensions. How would I do this? CG. So instead of having just a scalar input, if I had a multivariate input, multi-dimensional inputs, how would I do it? You guys, Saitya?
Do we need both perceptron domains?
So no, I'm speaking of one hidden layer. So here's what you would have to do it. It's not very easy. Guys, wake up. Remember, for higher dimensions, I can produce a cylinder, correct? And so I can create any function at all that I want by filling it up with cylinders and raising them to the right height. Okay? So here's your fourth pole. सवाल नहीं है क्या प्याजा पे देख नहीं रहे बच्चे they're not watching ठीक है तो ठीक 5 सेकंड एक्स्ट्रा दे देना all right 10 seconds guys okay stop it it's a simple poll right any real valued function can be modeled exactly by a one hidden layer network with infinite neurons in the hidden layer true or false how many of you thought it was true how many of you thought it was false you guys are right because what did we say it was Owen why is it false
Actually, I got this wrong.
okay somebody who got it right why is it false Shreya
Because it's just approximate.
it's an approximation you can get an arbitrarily precise approximation but there are regions of the input space where the output will be wrong no matter how large you make it even with infinite neurons it's going to be wrong somewhere right so now there's a discussion of depth versus width. The previous discussion showed that a single hidden layer MLP is a universal function approximator. Right? You can approximate any function to arbitrary precision, but we may require infinite neurons. More generally, deeper networks will require far fewer neurons for the same approximation error. This is true for Boolean functions, it's true for classifiers, it's true for real valued functions, it's true for all of them. But there are restrictions. Let's go back and look at this guy, right? Now, this decision boundary, we saw that we can model it using this two hidden layer network to the left with 16 neurons in the first layer and 40 neurons in the second layer, right? And if I do that, I can get this decision boundary perfectly with no error. But now, what will happen if I have fewer than 16 neurons in the first layer? Can I get it? Can I compensate for it by having one, doubling or quadrupling the number of neurons in the second layer? So you're nodding your head left and right. I don't see your name. What's your name? You. Yeah. I can't hear you. I'm sorry. But why can I not do it?
Because because the number of the classifier is just declare this number and we cannot separate them.
Exactly. So here's what happens, right? If I have only 8 neurons in the first layer, I cannot represent this pattern exactly. And why is that? Here is the kind of decision boundary that we will get. The 8 neurons, if I'm using threshold activation functions, the 8 neurons will capture 8 lines. So by the time you get past the first layer, the only information, the outputs of the 8 neurons will partition the input into the kind of pattern that I have in the top right. So the only information that you're going to get from the output of the first layer at this point is which of these 1, 2, 3, 4, 5, 6, 7, 8, 9 strips you're in, but it has no information about where you are within the strip. So that means that the information is gone. It doesn't matter whether you add 1 trillion neurons thereafter, you are not going to be able to recover the desired pattern, right? Now you might say I'm cheating because I made them all of these 8 lines parallel. What if those 8 lines were like a grid? The answer remains the same, right? The only thing that you will be able to do with the output of these neurons is to decide in which of the grid cells you currently are, but you can't say where you are in the grid cell. And so that information is lost. You cannot actually reconstruct the complete decision boundary simply by blowing up the number of neurons in your network downstream. And so it's not just that, the first layers. Let's say I have all 16 neurons in my first layer, but I have only 35 neurons in the second layer. Will I be able to reconstruct this pattern? In this particular example, because there are things that are shared, I think you could, but more generally you can see that you cannot, right? I will be missing some of the boxes. So what this means is, it doesn't matter that I have, I could have many more than 16 neurons in the first layer. If it's finite, then restricting the size of the second layer could ensure that I cannot model my function, right? So why is this happening over here? Why this is happening is because of a simple artifice that I forced on you in the past 2 classes. That's because I'm assuming that we are using threshold activations. A threshold activation is going to tell you whether you're to the left of a boundary or to the right, but it doesn't tell you how far you are from the boundary, correct? So it gates information in the input from the other subsequent layers, and therefore therefore you cannot make distinctions. So here, if I used a threshold activation with just 4 neurons, all you will be able to say is in which of those colored regions you are in, but you can't say where you are within those regions, and so you can't make further distinctions. So how would you fix this? Fun.
Maybe have some other parameters for the distance.
Dishan? Okay. Anybody want to guess? Yes.
Real valued inputs will help us understand where we are within the region, and then we can, in the next layer.
So you don't want Boolean outputs. You want to have graded activation functions, like a sigmoid. A sigmoid is not only going to tell you which side of the boundary you're in, it's going to give you some indication of how far you are from the boundary. Now you have more information downstream, and subsequent layers can use that information to build up more complex decision boundaries, right? But then, is a sigmoid good enough? Take a look. In a sigmoid, by the time I get here, the thing is saturated, right? So it continues to give information about how far you are from the boundary for a very small period of, a small range of the input. And beyond that, it saturates. So what kind of activations would you need that actually maximizes your ability of later layers to capture information that the earlier layers missed? Ideally, the activation must continue to tell you how far you are from the boundary, no matter how far you are from the boundary. A threshold doesn't do it, even a sigmoid doesn't do it, right? So something like a rectified linear unit, which is this guy here, that will continue to tell you which side you are on the how far you are from the boundary, but only on one side. An ideal activation would continue to give information on both sides. So maybe something like this guy over here, the so-called leaky ReLU or soft versions of it. So you will find when we work that there are different kinds of activation functions that you can use, but the activation functions that give you the greatest ability to learn functions are those that give you the most information about how far you are from the boundary on both sides of the boundary. At the least, you need to have information on one side of the boundary, which is why rectified linear units have become so popular, because they continue to give you information all the way out to infinity. Right? So yes.
But then why not have ReLU on the other side also? Why have leaky ReLU or something which is not...
If it's 45 degrees, right, then that's linear. Then the point of having layers vanishes, because when you have many layers of linear activations, it's like having one layer of linear activations. The only functions you can model are linear. So narrow layers can still pass information to subsequent layers if the activation function is sufficiently graded. But we will, if I make the lower layers narrow, I'm going to need more depth to compensate for the loss of information. But then there's another problem that actually happens over here, which is as you reduce the width of the lower layers, there's some other factor that kicks in, which is related to luck and your optimization algorithm. If I have only 4 neurons in the first layer, I'm as likely as not to capture these 4 parallel lines or something like it. So information that's transverse to these lines, I'm never going to recover. So as you can see, if you increase the dimensionality of the input, this problem is going to get more and more serious. And so when you actually reduce, although having fewer neurons in lower layers has some benefits, as we will see later in the course, a lot of benefits, you run the alternate risk that being able to find the function and making sure that these neurons end up representing meaningful boundaries such that the patterns can be composed later becomes a challenge. Right? So here's your final poll.
Professor?
Yes.
One of the selections in the poll is just networks with. It's just 2 words.
Oh, then they made a mistake. Here's the poll with the answers, right? Yeah. So a network with an upper bound on layer width cannot model any function by making it deep, right? There might be some functions it can never model. We already saw that. You can improve the approximation by adding depth, but there's some things it can never model. Yes, Shreya?
I had a question. Softmax is it's pretty popular as an application function. Is it that after that threshold, after that width, that you kind of don't care how far away from the...
We'll get to softmaxes in coming classes. Softmaxes are basically generally only used at the final layer to compute probabilities. So the sigmoid activation is an instance of the softmax. A threshold activation, you can think of it as saying it belongs to this class or it doesn't belong to this class. You can think of the sigmoid output as saying, here's the probability that it belongs to this class. We'll see that in the next class, right? Networks with graded activation functions are more able to compensate for insufficient width through depth. This we agreed, right? Now, we can always compensate for limits in the width and depth of the network by using more graded activations. No, you cannot make any claims about always. It just improves your chances, right? We have proved nothing that it's always possible. For a given accuracy of modeling a function, network with more graded activations will generally be smaller than those with less graded activations because you're conveying more information through the network. Right. Questions, anybody? Any questions? Yes?
Did you explain how and why we cannot just extend the network depth infinitely?
You could. Infinite depth is not a feasibility, right? But you can make them very deep. The latest networks are thousands of layers deep. There are other issues that come in. We'll get into that later in the course. So there's the whole concept of the capacity of a network. What can it model? And it has various definitions. We have something like information and storage capacity, how many patterns it can remember, VC dimension, which is bounded by the square of the number of weights in the network. From our perspective, the capacity of a network is the number of disconnected regions it can model, disconnected convex regions it can model. That gives us more of an intuition. And a network with insufficient capacity simply cannot exactly model a function that requires a larger minimal number of convex hulls than the capacity of the network itself. So we can approximate any function with error, but how well it can approximate a function is going to be limited by the capacity of the network itself. Now, there's a lot of work on quantifying the capacity of the network. This Koiron and Sontag's work from '98, Bartlett's work from 2017. Gerald Friedland and Krell have some very nice description of how you can think of it in information theoretic terms. And if I actually end up having an extra slot, maybe Gerald will do a guest lecture for us. So here are the lessons for today. MLPs are universal Boolean functions. They're universal classifiers. They are universal function approximators. A single or more generally a fixed number of layers MLP can approximate anything to arbitrary precision, but could be exponentially or even infinitely large. Deeper MLPs can achieve the same precision with far fewer neurons, far fewer parameters. Deeper networks are therefore more expressive, and more graded activation functions result in more expressive networks. So that's the end of today. We've seen that MLPs can emulate any function, but how do you can is not the same as do. So how do you actually make the network emulate a specific desired function? For example, you want a net function that takes in an image and produces a caption or labels all the objects in it. How do you construct this network? So this is the business of training a network, and we will begin talking about it next week. Questions, anyone? Thank you.